let's begin. So what if I told you, imagine that you take an image of a galaxy and simultaneously at the same time you collect the spectra. And instead of doing this analysis of this galaxy separately via some image analysis algorithm or via some spectral analysis, you develop a framework where you could put them together. Because the underlying physics is the same. It's the same object. Or imagine, instead of a single galaxy, you could do it over a patch of sky, where you observe some images and you do some spectral analysis of a patch of a sky. And instead of joint, separate networks, neural net, you could just take a single neural net that could take in these different formats of data. They are called different modalities. You combine them and get a very rich representation. Wouldn't that be interesting? And that's exactly the idea of CLIP model. So before we actually go into this paper, I guess we should discuss a little bit about CLIP. And to go to CLIP, I guess we better take a look into the paper. Okay, let's share the paper. Yeah, so here we are back again with this CLIP paper, actually presented by OpenAI. The idea came before this, but this was almost like a seminal paper in machine learning community. By the way, before we go into the paper, in this channel here I will discuss mostly papers, recent advancements in applications of AI in astrophysics. It's kind of thing, it's something that I actually do. Also personally, I think that we are in a beautiful time. It's an extremely exciting time where actually we could combine these things. We are in the era of abundant data. We're going to have many data. And to do the analysis, we need actually very advanced deep learning algorithms. And this work, the paper that we will discuss, actually uses one of these advanced algorithms, CLIP. So without any detail, let's get into CLIP. Let's start. So the paper title is a bit weird. It says learning transferable visual models from natural language supervision. Now, if I go down, what you will see here is the representative CLIP paper, image. So usually what we use this in, say, some slides when we present, the idea here essentially is that you have created a dataset, a joint dataset of images and corresponding descriptions of text. So let's say a brown dog jumping over a fence, or fish in your home aquarium, okay, etc. Now the idea here is that you basically have two different neural nets. One is trying to understand the image. You think of this as like an image encoder, and then you have the corresponding text description that's actually trying to understand the text, what's going on. So now you have these two different representation, and they are representing the same thing. Now they pass through these two different networks. They're called this image encoder and a text encoder. Encoding you can think of as something like you have this relatively large data. So let's say if I take an image of 1000 by 1000, when I do the encoding, I try to compress the data. Similarly, you can think of text. I have a huge description of text. I somehow want to compress it. So when I do reach into this compressed representation, at that point, what we do is we try to make the image and the text pair that are actually true, combine them together. So how do they do it? In the description, there is a very nice text. So here you will see, So first they curate this dataset with n image text pairs. And then of course, you have n image, that means you have n times n possible combination. So n square combination. But of course, n square, so most of them will be fake, because when you randomly combine, so you have an image of a dog and then you have a description that some cat hunting a mouse. That will not work, because the idea is that the image and text they should represent, and we somehow should be able to combine. So out of those n square, here they mention that n square minus n are essentially the incorrect pairing, because n is the original correct pairing. So n squared is the total number of combination. So number of incorrect pairings is n squared minus n. And now at this point, we have this representative set of true and false. So n image text pair that actually represent what it is in the image. The text represents what actually the image describes. And the other n squared minus n, they are basically trying to confuse the network. They're trying to pass some information which is actually not there, fake information. Now the idea of the clip is very cool. So now you have this joint representations of this image and text via this encoder. The idea is that you try to bring the pairs that represent the truth close together, and the ones that are fake, you want to push them apart. And that is very cool. Good thing is that when OpenAI was actually open, they are not open anymore, but when they are actually open, they used to write very, very well described paper. So here they gave a short algorithm to understand clip. So let's go through this few lines of prototype codes. So let's say I start off with this image I, and this image I is encoded via this neural net. It's an image encoder. It's like a compressed representation of image. And this is represented by this I of F. Similarly, we have the corresponding text encoder that compress the text T into TEF. And then you do a dot product. So what you are seeing here is that we are taking a dot product of the image and their corresponding projection. Okay, so we have this dot product between this I of F, this image encoder output, with this learned projection of the image to embedding. Okay, similarly we do the same for the text. Now once we have this, at this point we go back to bachelor's level first year physics. So now we have this two compressed representation. We are essentially trying to find the angle between these two compressed vectors. So let's say these vectors could have dimension something like 512, 1024, we don't know how many, but way more than 2. So it's a bit difficult to visualize, but you can think just as like a 2D vector. So the idea of two vectors that are representing the same information, you can think of them as two vectors pointing in the same direction. They're parallel. And when vectors are parallel, the angle between them is essentially 0. When the angle between them is essentially 0, what you are left with at that point is cosine of 0 is 1. And cosine of 90 degrees, when the vectors are perpendicular, orthogonal, cosine of 90 is basically 0. So now, when two vectors, it doesn't matter now how many dimensions they have, when the dot product of those two vectors are close to 1, those two vectors are kind of representing the same thing. And that's essentially the idea of cosine similarity. We have two vectors, we want to figure out how similar those vectors are. So now back to looking at this, you can think of this as a compressed representation of the image as a vector, compressed representation of the text as a vector, and then essentially you're trying to figure out how close they are. And that is essentially measured by cosine similarity. And that's the idea of CLIP, contrastive learning. We bring the images and text that are representative of each other, bring them close together, and the ones that are not representative of each other, image of a dog, text description of a cat, we push them far away. Now on the process of this, the idea is that the network, this whole network learns something very rich. So in the CLIP paper, what actually they show is something very weird. Before we go to the some example of CLIP in real life, because at this point you might be thinking, okay, this sounds very cool. We have an image and text description. We somehow try to align them, but where can we actually use it? So one idea, of course, that naturally comes to mind, because all of you are using ChatGPT or DALI. Well, it's not DALI anymore. It's it's included in ChatGPT already, or something like, let's say, Nano Banana within Gemini or Midjourney. So the idea is that you give some text description and it generates a beautiful image. So somehow there is this representation that takes you from text to images. So of course, one idea or one example of CLIP that naturally comes to mind, because we use them so often, this image generation model from text. But before I take you through some other beautiful examples here, I must mention that the dataset they use is actually insanely huge. Of course, if you just read the abstract, you're going to see the number. They mention somewhere about, yeah, here, 400 million image text pairs collected from the internet. Now, of course, major concern should appear that who gave OpenAI the right to use these images and corresponding text description. Okay. Okay. Let's discuss this some other time. Now that we have this true image and text pair representation, so you can think of this if I randomly combine them. So I have basically a data set of 400 million square data set, because in text image pair, when I randomly combine, I can have n square representation. Then they say this after pre-training. So pre-training, you can think of this as learning this encoded representation of the image and text. Natural language is used to reference learned visual concepts, enabling zero-shot transfer of the model to the downstream task. And that's essentially the idea of how can we use CLIP. So you learn this joint representation, and we could actually use it to do some amazing downstream tasks. So one of the examples that they show is this image classification. And by the way, what does this zero shot mean? Zero shot essentially means that you have this trained big deep neural net, and then you pass some data. and the network has never seen the data. So let's say I pass an image of a hippopotamus, and the neural net is trained on images and text of dogs and cats. So of course it has no clue of hippopotamus and the corresponding text description. And the idea is that if I just pass it some examples of a hippopotamus and a wolf, the idea is that the network will put the wolf close to the dog. So you think of this as like a huge vector space. So you have a compressed representation of this dog within this vector space, and you pass this wolf that the network has never seen. The compressed representation of the wolf will be close to the dog, and the hippopotamus will be far away because it doesn't match with, let's say, either dog or wolf. And that way we could actually use these models to classify images. Now suddenly I have, let's say, a labeling scheme where I label wolf that is close to dog as 0 and the hippopotamus that is farther away in this embedded space, okay, in this compressed space. When this vector, actually the compressed vector from this hippopotamus is farther away from the wolf, I label it as 1. So wolf is 0 and hippopotamus is 1. Now suddenly I have a classification system. And that's what actually they use the CLIP model. They show that when we combine images and text pairs and we learn the joint representation, we could use this model. So this is pre-trained to learn some representation between image and text. Then we could use it to do classification. So if you're into machine learning, if you're into deep learning, computer vision, they have this very famous dataset called ImageNet, and they perform this classification task on ImageNet dataset. So here they give examples of zero-shot transfer learning. So transfer learning, you train a network, you freeze it, all the weights in the models are frozen, and then you pass some other data that the network has never seen. Usually in the case of transfer learning, we can think of something like a fine-tuning. So we could fine-tune the model to do some further specific task. In the case of zero-shot, no fine-tuning, you just pass the data and the model somehow able to do some task. And in this case, it's classification. And they show some extremely cool results on the ImageNet dataset compared to some other models like Visual Ngram and etc. So that's essentially the idea of CLIP. So to summarize what's going on in CLIP, you have this image and text representation. There are two different mode of data. One is basically an array of pixels representing some pixel values, and the other one is some text. Okay, so there are two different modalities of data, but they are combined to learn a joint representation. Now that is very cool. Once learned, we could actually use it to do some different tasks. And this is now take us, I should probably touch a bit. Maybe the video length will be too long, but I guess I should touch a little bit. So this is essentially the idea of something like you could think of like a foundation model. We are heading into an era of foundation models, or rather more like a generalized model, where you have different modalities of data combined together, and then you have this big model that could do many different tasks. Something like, let's say, current ChatGPT, you could give an image, okay, it could make it blurry, it could make it sharp, you could give a text and it could summarize, and it could give you, it could expand the text, you give some audio, it could give you a summary of the audio clip. So you have these different modalities of data, but you get output from the same model. So ChatGPT is pre-trained, it's running somewhere in some server, in some data center, you put whatever formats of data, and it gives you output back whatever you need, most of the times very well. That's essentially the idea of foundation model. You have this big giant model trained with enormous amount of data of different modalities, and now that works, should I say this, that works as like a brain, okay, that has learned representation between these different modalities of data. Okay, now we could actually get back to the paper. Okay, let's try. By the way, before I go, I should go to the paper. I should tell you that there will be many videos like this because I like to read papers. I of course love to teach. So you're gonna see many videos like this where we go over papers and describe the idea of the paper that it tries to convey, and then probably relate it to something else. Of course, in my case, it would be mostly, let's say, applications of AI in astrophysics, because that's what I mostly work on. But if you want specific astrophysics topic or AI topics, you could put a request and I will try to cover them. Okay, now let's get back to the paper. Okay, so we are back. So I guess now we are diving into applications of this very cool idea of CLIP in astrophysics data. So if you read the title, a cross-modal foundation model for galaxies. So we already kind of touched upon cross-modality, like different modalities of data, text and image. And of course, we touched upon foundation model. Now this they present as a foundation model for galaxies. So how does it work? By the way, all of the papers that I have described so far, so let's say the CLIP paper, the foundation model idea was actually came from a group from Stanford. So I will also refer that paper down below in the description section. And of course, this AstroCLIP paper, it's a beautiful paper. I just recommend, if you're interested in learning physics and AI in general, just take a look at the paper by yourself. Okay, let's get back into this. Okay, so In the abstract, they say that, okay, we present this model AstroCLIP, a single versatile model that can embed. So here comes this idea of this embedding, like a compressed representation. Whenever you think of embedding, oh, my cat is here. Yo, you want to say hello? Hello, look at this. Okay. This is what you get in real life. Okay, so you have this single versatile model that's trying to embed this galaxy image and spectra. So once again, embedding is like a compressed representation. And look at this, into a shared physically meaningful latent space. So latent space is like a compressed vector representation. So let's say, I guess most of you, whoever you're watching this video, I'm pretty sure you must have some interest in machine learning and deep learning, otherwise why the hell you will be here. So I guess you already know the idea of latent space, but just for other people, or let's say younger audience, the way you can think of this, let's say I start off with this images taken from iPhone. So these are essentially extremely high resolution. Let's just take an example. So let's say 2000 pixels in the width and 1000 pixels in height. So that's a tons of pixels, like almost like 100,000 pixels, 200,000 pixels, right? So we need this 200,000 pixels to convey the information in the image. Now the idea of the latent space is like we compress this into a much smaller vector, something like, let's say 1024, maybe 8,000. So now we went from this 200,000 pixel space, we got down to this 8,000 or 2,000 or 4,000 vector space. So of course this is a way more compressed representation, and that's the idea of the latent space, where we have compressed the information but it's extremely rich. So single versatile model that can embed both galaxy images and spectra into a shared physically meaningful latent space. These embeddings, this learned representation, can be used without any model fine-tuning. So back again to fine-tuning we just described before. You train a model for some particular task with some particular data set. So let's say I train a model to classify dog and cats, and then I pass images of birds. The idea of fine-tuning is that, let's say my model has way too many layers. So that's the idea of deep neural net. I have many layers of nonlinear calculation performing layers, okay, stacked on top of each other, and we freeze almost all the top layers and we fine-tune the final layers, and then we pass the images of birds and whatever, let's say some insects, okay. And then the idea is that with the fine-tuning, now we could use this pre-trained model that was initially trained to classify dogs and cats with this fine-tuning by just slightly adjusting the weights of the final few layers. Now the model is performing extremely good to classify dogs, cats, birds and insects. Okay, so that's the idea of fine-tuning. So here they mention that they don't do any fine-tuning. That's the idea of back to this zero-shot learning. No fine-tuning, you just pass the data and the model learns something, okay? Without any model fine-tuning for a variety of downstream tasks. So here comes the example of this model in astrophysical data analysis. Accurate in-modality and cross-modality semantic similarity search. In-modality, so within the images. Cross-modality, images and spectra. Photometric redshift estimation. So we take images of galaxies. Basically, you can think of this as like, these are representations of photons that are hitting the detector. So the images, so the pixel values are basically, you can think of this very, very abruptly as like some sort of photon count estimator. So from this, and different filters in front of the telescope, we could do something like a photometric redshift. Okay, but that's not so accurate. What's actually accurate is something called a spectroscopic redshift. We take the spectra of the galaxy. We know exactly under the lab setting, let's say, where will be the hydrogen spectral emission line or absorption line. And then we compare what we see from what's coming from this galaxy. And then this line would be shifted most of the times to the higher redshift region. And from that, we could get an idea how far this galaxy is. That's essentially the idea of redshift. When we calculate the redshift from analyzing spectra of the galaxy, that's way more accurate than photometric. Now, doing spectroscopic analysis and doing spectroscopic search is way more time consuming, resource consuming than compared to photometric. So most of the times we're going to have photometric data and not spectroscopic data. So the idea is very cool. Let's say if I have some photometric data and I could give you an estimate of spectroscopic redshift and I don't need to do spectroscopic measurement, that's voila. Oh my God, that's a big improvement. We don't need to use a lot of resources with telescopes, management, analysis of the data after collecting data. We could just use the photometric model, okay? So, oh my God, this video is going to be long. Photometric redshift estimation and galaxy property estimation. So what they essentially show is something like, let's say, the stellar mass of the galaxy. What's the star formation rate in the galaxy? Just from the images and spectra. And then some classification, whether the galaxy has some bulges, within the galaxy is disc-like, within the galaxy has a bar-like shape, and etc, etc. So let's look at I highlighted the paper, so this is how I usually read. But anyway, let's go to the most representative part of the paper, which is the image like what you have seen before in CLIP. So let's look at this. So now we have this. Sorry, it's my cat. So now we have this joint space of image and spectra. So, by the way, they collect the data from this dark energy spectroscopic survey. So I think here they mention our methodology to optical spectra from dark energy spectroscopic survey and multiband images from legacy imaging survey. So that's how they create this image and spectra pair. I think they give some number about 100,000 pairs that they have with proper images and correct spectral measurement. So now you have these two different encoders. Now you see the similarity between CLIP and AstroCLIP. So you have this galaxy image encoding going on to take you to a compressed space, and then you have the corresponding spectra that will take you to a corresponding compressed space. And then, of course, you do the same shuffling. N true representation and n square minus n false representation. You bring the true representation together, you push away the false representation farther apart. Then on the downstream task, you put some galaxy images, okay? So from images, we can have photometric redshift idea. Now, from the compressed representation of this image, we have an idea of how close it is to some other galaxy information. Now, this representation space contains both when it was trained. That is on the left-hand side. When it is trained, you have both images and spectra information. Now, during the test time, I have only, let's say, the image. I pass the image. Now I find what's the closest vector of this compressed representation of the image to some spectral vector. And that would actually help me to give an estimate of the spectroscopic redshift. And then they show that this works extremely well. So they make some very nice plots on this. Too much description on the data set, and it has to be like this because you must know where your data come from, what are the limitations, how the model is prepared is a very, very important factor, of course, to reproduce the work. And of course, and by the way, this model is completely public, so if you're interested, you could just try. Shout out to the author. I think it's Liam Parker, Franco Alanuse, and some amazing group of people. It's actually this polymatic AI collaboration that wrote the paper. Okay, let's get to this very nice image of estimating redshift. So here you see in the prediction and true, they line up extremely well. So this photometric spectroscopic redshift estimation is really, really good. And then they also show some other downstream tasks, like just from images and spectra separately, whether I could actually measure the star formation rate in this galaxy, then what is the mass weighted galaxy age, and other stuffs. They also show the classification performance. Let me show you the picture. Here's a very nice picture of this. Yeah, exactly. So you have this different morphology of galaxies, right? From their shapes, you could do some classification, like spiral arms, bar-shaped. If it has a bulge, edge-on bulge, and you see that most of the times AstroCLIP performs almost like over 70%, 80%. So this is just really nice classification. So you have this pre-trained model, pass the images of galaxy, and then it could do a zero-shot classification. Really cool paper. And coming to the conclusion, what they mention is that they demonstrate the potential. I would say that not only they demonstrate, but they actually inspire people like us to work on this. So they demonstrate potential for cross-modal contrastive pre-training, right? So that's the idea of contrastive pre-training. Galaxy image spectra that are representative of each other, bring them together. Galaxy image and spectra that are not representative of each other, put them away. We have this contrast now. CLIP, contrastive learning, okay? Contrastive pre-training to achieve high-quality foundation models. So now you have this shared representation space, which is extremely rich. And now I could do many downstream tasks. You see the comparison with ChatGPT? I could do many downstream tasks. I could estimate the mass of the galaxy, star formation rate of the galaxy. I could classify galaxy depending on their how they show up in the images. Okay, so you think about this. The model was not explicitly trained to do the task. The model was trained to just learn the representation of images and the spectra and bring them together when they are representative. That is so cool, okay? That is super cool. Okay, so this includes accurate in-model and cross-modal semantic similarity search, photometric redshift estimation, galaxy morphology classification, and etc. And that's it. Excellent paper, by the way. I mean, it's probably a disservice to go over this paper in 10 minutes. I don't know how much time I spent, but I guess this video is getting insanely longer. And I wanted to give you an overview of, let me get back to the full screen. I wanted to give you an overview of the AI model idea and then how it is actually used in this astrophysics context. I strongly recommend, just if you're really interested, go and take a look at the paper. The GitHub is also public for this paper. They made everything public. Most of the data that are used, they're also publicly available. So essentially, if you are really interested, like doing some citizen science or something, you could do something similar. And I hope that astrophysics and in general particle physics or astrophysics group, hopefully we will remain to be open, where we will still share all our codes and will not become like OpenAI. None of us, we don't know what the hell is going on with ChatGPT 5, what kind of data was used, what are the model, and etc. Until and unless some scientist from the company that comes up and say something, we know nothing, even though it was supposed to be open. Okay. I hope this video was informative. You liked it. If you want some specific topics, put it in the comments and I'll try to get back. Thank you, everybody.